My name is Mitri, and I'm going to present my paper called Difference-of-Estimated-Densities-based Positive-Unlabeled Learning. So what is Positive-Unlabeled Learning? Well, I'm going to start with supervised classification. Here we have data from two classes, positive and negative, and what we want to find is this decision boundary that separates the two classes. On the other hand, in one class classification, we only have positive data, and we want to find again decision boundary that separates it from all possible anomalies. And then positive-unlabeled classification is kind of in between these two cases. Here we also have positive data, and while we don't have clean negative data, we have an unlabeled mixture of positive and negative data. And we still want to find the same decision boundary as we would in supervised classification. Positive-unlabeled learning is applied, for instance, in anomaly detection of time series and texts, in biology and medicine, for instance, for disease gene recognition, as well as some cases beyond classification, such as recommender systems or learning word embeddings. Let's talk a little bit about the goal of PGU learning. The claim is that while we only see positive and unlabeled data, what we want to do is to restore kind of this picture that unlabeled data is actually either positive or negative. And two steps to this are, first step is to estimate the proportion of positives in the unlabeled data, or priors, share. Either way, it's going to be denoted as alpha. In this example, we have 40 unlabeled dots, and 20 of them are positive. So alpha is equal to 0.5, and we want to estimate it as 0.5. And the second step is to estimate posteriors that a concrete unlabeled distance is positive rather than negative. It's going to be denoted as probability of being positive, well, of x, which is the instance. In this example, here on the bottom, the points are kind of around blue circles, so there's a lot of positive data, so this is probably positive. And then above here, there's not much positive data around, so this is probably negative. And in between, we're kind of uncertain. These points might be positive or negative. In fact, they are either positive or negative. We're not really sure which is which, so we're uncertain. This is what we want to obtain, the probabilities. So we can't always obtain the hard labels, but the soft probabilities are what we aim to find. Now, the methods that solve these two problems, I'm going to talk about two such methods. One is proposed in 2008 by Elkan and Noto. And this is based on non-traditional classifier. What is NTC? So it's just any classifier like a neural network or SVM or any other classifier that distinguishes positive data from unlabeled data. And the method that they propose looks like this. First, we take our positive sample, which are ones in this example, and unlabeled sample, which is a mixture of zeros and ones. We train a non-traditional classifier to distinguish the two by obtaining the predictions of such classifier for each data instance. So here, for example, 0.71 represents the probability that this one belongs to the set of the positive instances, which is ones, rather than unlabeled instances of zeros and ones. And we can convert this very easily to the unbiased probability that it's either a 0 or a 1 using two simple equations. I'm not going to stop with them for too long. What's important is that, well, the notion of non-traditional classifier and the properties of this method, which are first that it estimates both priors and posteriors, which is great, but it doesn't usually work that well in practice due to this assumption that these predictions are well-calibrated probabilities. They are usually not, and this usually underperforms. Now, another method is considered state-of-the-art. It's based on unbiased risk estimation. And the idea is to train a neural network on a modified loss function that approximates negative risk as a difference of unlabeled and positive risks. Now, this method does achieve good performance and is considered state-of-the-art. However, it assumes that alpha is identified in advance, which is a definite limitation. Now moving on to our method, named DEDPUL, It is based on bias rule at the traditional classifier and expectation maximization. And we're going to talk about how this all ties into one coherent singular method. And DEDPUL, it does outperform the previous state of the art, as well as it estimates both priors and posteriors, so it doesn't assume alpha to be identified. So how does it work? First, we'll start with the bias rule. And here's on the right is a little reminder that in the bias rule we have posterior probability, and it can be decomposed as priors times likelihood divided by evidence. In our problem, the posteriors are, well, that x is positive. It can be decomposed as alpha, which is the prior probability, times the likelihood, which is the probability density function of positive data, or in short, positive density. It's going to be denoted as f, and here p denotes positives. And in the bottom we have the same term for the positive data, and then another term for the negative data. Now the main insight is that, well, we could want to estimate these two densities from the samples. However, we don't have the sample for the negative data. We only have positives and unlabeled data. But this denominator is exactly the density of the mixture, so of the unlabeled data. Once we rewrite this formula like this, okay, now we have samples from the numerator and from denominator. Can we just estimate these densities from the samples and then receive the posteriors and solve the problem? Well, there are two definite and obvious downsides. One is the curse of dimensionality. What affects is very multidimensional, like a picture. Then it's complicated to estimate this density. And the other problem is obviously estimation of alpha. Now we're going to discuss how to solve these two problems, and we're going to have DEDPUL. First problem, curse of dimensionality. The crucial insight proven in the paper is formulated in this lemma. It basically means that instead of taking our initial bias rule, where densities are over the x, the multidimensional initial data, we can replace these densities with densities of y, which is the prediction of non-traditional classifier. And y is one-dimensional, it's just a probability, so estimating these densities is much easier. Not only it is easier, but it's equivalent to estimating the ratio of the initial data. So this is very convenient. And I have to mention that it has been known in the literature that non-traditional classifier preserves priors, but this formula that it preserves the posteriors has not been known before, and is proven in the paper. Then the pipeline looks like this. We have seen the top row that our data is transformed to one-dimensional predictions of non-traditional classifier. But then, unlike Elkan and Noto, we estimate the density functions of these two prediction vectors. And it often looks like this. So here we have the positive density that has one distinct mode, and then labeled density that has two distinct modes. One, of course, corresponding to the positive data, and the other corresponding to the negative data. And heuristically, you can already see that this on the right is probably the positive data, and this on the left is probably the negative data. But the correct way is to put this ratio of these densities into the bias rule, multiplied by alpha, and then compute the exact posterior probability, which is unbiased. Here's also a little clipping operator just to ensure that this probability is bounded in a 0-1 interval. The only thing left is estimation of this alpha of the priors. And the way we're going to do it is we're going to use expectation maximization to choose such alpha that is equal to average posteriors. This method is based on a very simple definition of marginal probability, which is well known in general, which tells us that probability of x is equal to the probability of x conditional on y in expectation over y, which means that prior probability has to be equal to the expected posterior probability. So how do we apply this rule? First, it's going to be an in iterative algorithm, first we initialize alpha as 1. We put it in the bias rule alongside with the densities that we estimated. We obtain posteriors. We take average over posteriors. We get some number, which is usually lower than 1. We set alpha to this number, 0.8. We repeat. We get again lower number. We repeat this again. And you can see that both alpha and average posteriors become lower, as well as the margin between them. But the margin is still non-zero. So we repeat this for enough times, and hopefully we converge to some number, in this case 0.4, and choose this as our alpha, and it follows this rule, basically. I also want to mention that this thing is very computationally cheap because we already trained our classifier, we already estimated our densities, so this is very simple. 2 caveats. First, this alpha that we identify is non-unique. In fact, any alpha lower than 0.4 would also be as good as an answer. But the fact that we can only estimate upper bound is just a quirk of PU learning. There's no way around it. And the second caveat is that this might not converge. So in this case, it only converges at 0. And in these cases, we use alternative estimation, but I'm not going to discuss it for too long. So here's the pipeline then. We have seen this. We put data from non-traditional classifier, receive predictions, estimated densities, and then we alternate between 2 steps. First, the bias rule, and second, the estimation of alpha as average posteriors. We go back and forth until we converge. And we obtain both posteriors and alpha, and thus solve the problem. Moving on to experiments. First, the procedure. On the example of Cipher 10, this is the dataset that has pictures of animals and vehicles. First, we set some class as a positive, for instance, animals. Then we construct a mixture of animals and vehicles. And this is PU data, artificially constructed. We train on this data, but when we test, we evaluate on positive-negative labels. So it's either an animal or a vehicle. And then we separately evaluate estimation of priors and posteriors, because some methods only do one of these things and DEDPUL can do both. First, estimation of alpha. Here we will have 3 plots for 3 datasets. On the y-axis is average absolute error over 10 runs. So the lower, the better. On the x-axis is the true value of alpha, which we want to identify. And the methods are DEDPUL, black, 3 state-of-the-art methods, and Elkan and Noto, which is baseline, also based on non-traditional classifier. So here we can see that DEDPUL kind of performs better than all the methods, but the margin is not too high. But when we move on to MNIST or Cipher 10, which are more complicated datasets, we can see that other methods become much worse, whereas DEDPUL just performs well on all the problems. Moving on to estimation of posteriors, here as a metric we have chosen 1 minus accuracy, so again the lower the better. And the methods are DEDPUL, and then PU, which is based on unbiased risk estimation, which is previous state-of-the-art, and Elkan and Noto is a baseline. On the Y dataset, we can see that DEDPUL performs better than all the methods, but on more complicated image datasets, we can see that DEDPUL performs on par with state-of-the-art. However, keep in mind that DEDPUL also estimates proportions, whereas state-of-the-art assumes them to be identified. In conclusion, DEDPUL is based on bias rule, non-traditional classifier, and expectation maximization. This proposed method performs on par or better than state-of-the-art in both proportion estimation and estimation of posteriors. And as for the future work, we kind of want to develop our method further to internalize all these density and proportion estimation procedures into the classifier's training procedure, and we could also extend DEDPUL to related problems. That's it for me. Thank you for your attention. Please feel free to write me with any questions or comments. Thanks.